Chapter 21, Electromagnetic Induction, Part 2. Here, we look at transformers, its structure and principle of operation. So, the magnitude of the induced EMF and current can be controlled by the number of turns of a coil. So, the transformer can change from a high alternating voltage to a low alternating voltage and vice versa. This is an illustration of how a transformer looks like. First, you have the primary coil, denoted by small p, and secondary coil denoted by small s. The number of turns of the primary coil is given by Np and Ns for the secondary coil. The voltage for the primary coil, Vp, and Vs for the secondary coil. So all these are actually coiled around a laminated soft iron core, because a soft iron core is easily magnetized and demagnetized. Okay, now let's look at the formulas for a transformer. So, Vs is equals to Ns over Vp equals to Np. So this is the formula. On the right hand side, Ns over Np is actually the turn ratio of a transformer. So what we are using transformer for is to actually control the magnitude of the induced EMF and current so that we can step down from the power station to our houses and appliances and regulate the voltage. So if your Np is greater than Ns, which is the number of coils in the primary, is more than the number of coils in the secondary, your Vp will be greater than your Vs. And this is known as a step-down transformer, because you're stepping down the voltage. If your Np is less than Ns, your Vp will be less than Vs. It's known as a step-up transformer, stepping up the voltage. Okay, now let's look at the principle of conservation of energy. So it states that the power in the primary coil will be equal to the power in the secondary coil, because the input power is equal to the output power. In the previous chapter, we have learned that the formula for power is P equals to VI. So using this formula, we get Vp Ip equals to Vs Is. And combining this formula with the previous formula, you will get the combination of Vs over Vp equals to Ip over Is also equals to Ns over Np. And this is a combined formula for the whole of transformer. Okay, let's look at a work example. If a transformer has 500 turns in the primary coil, so Np, and 250 turns in the secondary coil, Ns, the primary coil is connected to an input voltage of 240 volts, Vp. Is it a step down or step up transformer? So since your Np is greater than Ns, it's a step down transformer with a ratio of 1:2. Remember that the ratio is Ns over Np. That is the turn ratio. So can we calculate the output voltage? You can just use the formula Vs equals to Ns over Np. And this is the formula we will use. Okay, let's look at the power transmission of a non-ideal transformer. In reality, transformers are definitely not ideal because there will be power loss. So how do we calculate the efficiency? We will use this formula, output power over input power times 100%. And that's efficiency. So this is how a transformer looks like. Okay, so what we do is that we burn the coal or fossil fuels from the power station. We step up the voltage across power lines. And when it comes to your house, we step down. And right before it reaches you for you to charge your phone or to charge your PLDs, we just step down the voltage again. Okay, due to resistance in the cable, we have something called Joule heating. So energy is lost in the form of thermal energy or heat. And this formula is given by the formula P equals to I square R. So to reduce loss through thermal energy, one way is that we can reduce the resistance in the cable. The formula R equals to rho L over A. So if we increase the thickness, we can reduce the resistance. However, this may lead to higher cable costs. Second method is to transmit at high voltage. Okay, so if you transmit at high voltage and low current, your power loss will be minimized. Okay, let's look at one last example. A 100 meters long transmission wire has a resistance of 0.005 ohms per meter. So length L, this is resistance per length. So find the power wasted in the line when 300 kilowatts of power is transmitted at 240 volts versus 1200,000 volts. So we can find the resistance first. So resistance was equals to the R over L times L. So you get 0.5 ohms. Using the formula P equals to VI, we can actually get the individual current at the different voltages. So we get current at 125 ampere for the 240 volts. At 120 k volts, the current is smaller. So we calculate using the formula P equals to I square R for power loss. You get this value, 7K versus 0.03 watts. So we realize that at higher current, the power loss is larger as compared to at lower current. And that is the end of this chapter.